This video was sponsored by Brilliant. The Duke Nukem source code will blow your mind, and I'm not even joking. In all the games I've reviewed thus far, I have never seen anything like this before. I still can't decide which part is more crazy, the story how the engine was created or the source code itself. So first let's start with Ken Silverman. The guy who single-handedly created a game engine, sent a demo to Apogee and got contracted to create an engine that will power their next big game. And all of that at the age of 17, before he even started college. You probably feel bad right now, and so did I. But don't worry, it's only going to get worse. It is the mid-90s. 3D Realms, a brand under Apogee, set out to create a game that will challenge id Software's doom. So they put their money where their mouth is and let the young self-taught prodigy Ken Silverman do his thing. Few years later, they released a title that will become known as the Doom Killer, Duke Nukem 3D. It raised the bar for technical standards back then with features like the portal system, flying around with a jetpack, interactive environments, and strippers. Under the hood, the Duke Nukem 3D source code is the epitome of genius chaos, a monolith of brilliance. It was not built to be readable or maintainable, it was built for raw power. This is Duke Nukem 3D. For the preparation of the video, I read id as Super Ego, the creation of Duke Nukem 3D, and Fabian Sanglar's blog posts, which is, in my opinion, the most credible source for understanding the engine, since it was proofread by Ken Silverman himself. I highly recommend reading both, and as always you can find the links for all my sources in the description. As you know, my videos have no filler content, so let's start with the roadmap of the video. First, we're gonna talk about the architecture and chaos by design. Then we're gonna talk about the engine internals, source code of the portal system, main loop, and rendering. We will also take a look at the game module source code, but the main focus will be on the engine part. Then we're gonna take a look at Ken Silverman's build info text file. Finally, we'll arrive at the conclusion and explore the key lessons we can learn from this project. Okay, so let's start with the architecture and chaos by design. Duke Nukem 3D was my first visit to a strip club, and in case my girlfriend is watching, babe, it was also my last time. And that was more than 20 years ago, in a game. It's not a real place, babe. We had this conversation. Okay, seems like I will be sleeping on the couch for the next few days, or weeks. Anyways, Duke Nukem 3D had strip clubs, which I never visited. I just heard people talking about that during the lunch break. So I guess we're gonna start with the architecture and looking for a blanket. Duke Nukem is split into two parts. The engine, which was called the build engine, and the game module. Now the engine is responsible for the rendition, networking, and everything the game needs to run. And the game module uses the services provided by the build engine. To understand why certain architectural decisions are made, you have to consider many factors. Some are technical limitations, others come from working with legacy code or building on top of older projects. And what many beginners don't realize is that some choices are driven by organizational factors. Things like team structure, deadlines, or company politics. What do I mean by that? Well, if a company decides to build a product but doesn't have the in-house capacity or simply chooses to outsource parts of the project, that decision can directly impact the software architecture. Not for technical reasons, but for practical ones, like aligning with external teams or managing handoff boundaries. Now in case of Duke, Ken Silverman was contracted by 3D Realms to create the engine part, and the game module was then done by the guys from 3D Realms. So they worked out a deal where Ken Silverman just provided a binary static library, the engine object file, and the engine header file. 3D Realms developed their game library, and then at the end they just linked the two object files together and created a Duke Nukem executable. This is a very common practice, and if you watched my other videos, like for example the Doom video, I explained in more detail how this compilation linking process works. And now comes the interesting part of the architecture. The engine is one large monster file with 8,500 lines of code. It has 10 master functions and 2 auxiliary files. Cache 1C, which contains cache system routines and a virtual file system, and A.C, which is a C reverse engineered implementation of a highly optimized assembly code. Then we also have the build.c and header files, which contain some map editor related stuff. And Ken Silverman also provided a build info text file, which is basically a manual on what each function does. We will go through this file later in the video. Okay, then we have the game module, which was done by 3D Realms. The game module was using the functions provided by the build engine for rendering, loading assets, and so on. The only exception is the sound, which was implemented in the game module. Now, the architecture of the game module is quite different than the one in the build engine. You will see much more modularity and even aspects for easier portability. But still, game.c has more than 11,000 lines of code, menu.c has 3,000 lines of switch case, and they use a lot of global variables. But overall, it is easier to follow and understand than the engine part. Now, another interesting fact is that these two libraries haven't been open sourced at the same time. The build engine was open sourced in the year 2000 and the game module in 2003. So the whole source code became available just 7 years after the game was initially released. Now, some general comment on this structure before I dive deep into the genius chaos of the engine. It does not make sense comparing this to, let's say, Quake 3. But if you compare it to Doom, for example, you will realize that Doom had a layered architecture and was more modular than the build engine. That's also a reason why Doom was more mod-friendly than Duke Nukem. Now, if you zoom out and compare these two projects, Doom and Duke Nukem, you can clearly see how different priorities shaped their architecture. For id Software, portability was a key concern. They had already shipped multiple titles and understood the value of planning for future ports early in the development, thinking ahead to questions like, how are we going to get this running on a Super Nintendo if Nintendo reaches out? And let me be clear, both approaches, in the grand scheme of things, have their advantages and disadvantages. Before we continue, let's hear from today's sponsor. Brilliant teaches you stuff while the rest of the internet waits for World War III like it's a season finale. Now, seriously, instead of doom scrolling, reading hot takes from people with flags in their bio, you can actually learn something useful, like logic, algorithms, neural networks, or quantum stuff. Brilliant makes learning feel easy, interactive, fast, and low-key addictive. No videos to zone out to, just real problem solving that wakes your brain up. I use it between meetings, while code compiles, or when the group chat is planning summer trips that will never happen. And the best thing is, it's not just for people with PhDs or 5 monitors. Lessons are built step by step. It's one of the few apps that actually respects your time. You open it for 5 minutes and boom, you're learning about stuff you didn't even know exists. Click on the exclusive link in the description or scan the QR code on the screen to try everything Brilliant has to offer for free for a full 30 days. You will also get 20% off an annual premium subscription. So yeah, instead of waiting for the world to end, you can learn stuff and become fun at parties. Back to the video. Now let's talk about the genius chaos. In the past I've talked about layered architectures, server-client architectures, microservices, and I expected something similar in the build engine. Some split between high level and low level, then we have some triggers that initiate an update of the game state via some event system, and eventually we get data structures that describe objects or entities being passed around with functions that return some values. But as I was analyzing the build engine and started putting all the pieces together, it became clear to me that this is some alien level sorcery. I'm gonna now outline the key concepts and design decisions of the build engine, and you will realize why these decisions made the engine specialized for raw power, notoriously hard to maintain, but most of all very interesting. Okay, the main philosophy of the build engine is we have a global game state. Almost everything is a global variable. Player position, current sector, view angle, list of faults, draw buffer, everything is stored in global variables. Now, what is happening on a low level when someone decides to define everything as global variables? When you compile a C program, the compiler places all your global variables to a specific section in the binary. Now, if the variable has an initial value, it goes to the data segment, if the variable has no initial value, it goes to the BSS segment. BSS means block started by symbol. This BSS segment doesn't even take up space in the binary file. It's just a note to the operating system saying allocate this much memory and fill it with zeros. So then when we launch the executable, the operating system loads the binary into memory, copies the data segment from the binary into the RAM, including all the global variables with initial values, allocates memory for the non-initialized global variables from the BSS segment and sets them to zeros. And finally, your binary starts running, with all your data already sitting in the memory, ready to go. Now, the prompt engineers are now wondering, why would anyone do this? Well, when we take into account that this was supposed to run on low-spec hardware from the 90s, it comes with few advantages. First, no memory allocation, no mallocs, no freeze, everything is allocated at the startup, so it comes with zero runtime allocation cost. The operating system handles everything while loading the game. Then no memory fragmentation, the memory layout is fixed and very predictable. It is very cache friendly since flat, one-dimensional, fixed-sized arrays are laid out in linear memory. And no indirection. Functions can read and write global data directly with no parameters. Okay, but what are the cons of this approach? Well, you can't resize anything at runtime, so you have to write everything bulletproof. You have no flexibility. And generally speaking, global state means functions are tightly coupled. They all depend on and manipulate shared memory. Ken Silverman decided to trade scalability and modularity for raw speed, which was the right choice at that time. Okay, so at the center of the build engine, we have the game state, which is defined with global variables. Now, the second big design concept is the logic of the whole engine is procedural, not object-oriented. So there's no OOP in build. I mean, C is not an object-oriented language per se, don't get me wrong, but you can still emulate object-oriented paradigms in C by using structs, function pointers, and by being disciplined about using specific design patterns. The engine is one big pile of functions and global data. As I said, this comes with performance advantages, but also some downsides like no encapsulation, no polymorphism, low reusability, and basically everything is allowed to touch anything. Now, the question is this really a bad thing? Well, let's put it this way. Ultimately, it is a trade-off at least. In my opinion, if you're not forced to use object-oriented programming, you should at least play with the idea of doing your program in a procedural manner. There are many use cases where it is a monster headache to squeeze something forcefully in an object-oriented frame. But we are taught at the university and coding tutorials that object-oriented programming is the way to do things. I strongly disagree with anyone who says that OOP is the best way to do things, but I also disagree that it's the most stupid way to do things. Generally speaking, nowadays we live in a world where everything is you are either on this team or on the other team. And nobody even asked you if you're interested in playing the game. You are either with us or against us. Sir, this is a C code review video. I'm into cold drinks, barbecue, and good weather. Anyways, back to the video. So the functions, as I said, are oftentimes not returning any value. They just take the parameters and manipulate directly the global data. So the build engine follows the design principle, the data is the interface. I would not recommend doing this on a large-scale project, since the debugging can be a nightmare, but on small embedded projects with only 50 lines of code application layer, this works fine. Of course it comes with all the disadvantages like no data protection, but if you know what you're doing, if it aligns with the scope of the project, I don't see an issue. Okay, the next design decision is build uses fixed point math only. So it's not using floating point, everything is integer based fixed point math. The advantage is it runs fast on older hardware without FPUs like the 486 for example. The disadvantage is self-explanatory, you have lower precision and you have to do manual scaling and shifting. Now, in some of my past videos I talked about using pre-computed lookup tables for trigonometry functions. Build uses lookup tables for these performance critical values like sine and cosine, scaling factors, and inverse distances. By doing it this way, on older hardware you get performance benefits. On new hardware it is not that much of an issue. But it still makes sense if an operation turns out to be in a code section that is performance critical and is a bottleneck. Okay, the next concept is the build engine is entirely single-threaded. It does not use multi-threading at all. I mean, this is a no-brainer since most computers at the time were single-core machines. But it also aligns with its global state design, so you don't need to worry about concurrency, everything runs sequentially in a single main loop. Which also makes it kinda more difficult to program since you have to align all the function calls in a perfect order. Now, another thing that I noticed is Ken Silverman used a lot of bitwise hacks for fast processing. For example, build uses bitwise operations for geometry logic. In this case, it checks if signs are different. It removes branching and is fast, but it also makes it hard to read, or at least not obvious from the jump what the person is trying to do. Okay, so these low-level design decisions made build extremely fast for its time. But as you can imagine, it also made it very hard to maintain, port or reuse. Still, it is a fascinating case study in performance-first engine design. And just in case it's still not clear how monumental this work is, or how insanely talented Ken Silverman was, just think about this for a second. He built an engine that had more advanced features than Doom, ran on low-end hardware, did it entirely solo with none of the modern knowledge or tools we take for granted today. No Stack Overflow, no ChatGPT, no Claude, no Cursor, no endless blog posts and tutorials. Just pure brainpower and maybe a couple of books. And here's the part that blows my mind. It's all procedural code. No objects, no classes, no clean abstractions. Just one giant web of functions and global variables. All tightly packed, interwoven, and somehow, miraculously, it works. But not just barely works. It runs fast, it's feature-rich, it's playable, and it's efficient as hell. On paper, this codebase should be a disaster, but it's not. It's a masterpiece of controlled chaos. But as they say, only a genius can rule over chaos. Or like Einstein said, an intelligent person controls chaos. A genius thrives in it. And Ken didn't just thrive, he dominated. Now, another thing I want to emphasize is that the end customer does not really care about how your code looks like, as long as the game application works properly. Now, before I go into the engine internals and code, I want to say a few words why Duke Nukem in terms of game design stood out during this early FPS era. When I was a kid, we were talking about the early 2000s, I remember Duke Nukem being the game with the best graphics and frame rate that my computer could run. There were better games out there, but my computer was so slow it couldn't run them properly. So my point is, you can have the cleanest code and architecture of all time, but if the game is boring, nobody will play it. Duke Nukem managed to grab people by the throat and make them pay attention. It stood out because the main character had a personality, and you had strippers of course. It didn't need to be clean or elegant, it just needed to be unforgettable, and that's exactly what it was. Now let's talk about the engine internals, main loop and rendering. So we're gonna start with the portal system. In comparison to Doom, which uses a BSP system for its maps, Duke uses a portal system. BSP trees were pre-processed, which came with a speed advantage, but a disadvantage was walls couldn't move. So in Duke the maps were not pre-processed and relied on this portal system. During the creation of a map, the game designer would draw sectors, which were made out of walls, and then set walls that are connecting two sectors as portals. So you get something like this. The result was an array for sectors and this array for walls. But how are these walls and portals and sectors defined in the code? Now, walls and sectors are defined in the build header file. So the sector struct looks like this. As you can see, there's not much explained in the comments, and also some of the variable names are not really self-explanatory. Like, what does extra mean, or what is low tag, high tag? But luckily enough, Ken Silverman delivered alongside of the source code, remember the build info text file, where we can find all these explanations. So if we open the info file, we can find the sector and wall struct, and then read the description for each member variable of the struct. Okay, now let's take a look at the main function. You will realize very fast why this codebase is very difficult to follow. So, of course, we start by defining IJKL and temp autorun. If you don't understand what IJKL stands for, then you're suffering from severe skill issues and are probably a prompt engineer whose guilty pleasure is watching my videos. We don't need comments. As someone said under one of my videos, code is the documentation, so we only need the code to understand what's happening here, right? Then it continues by setting the first element of the Todd array to T, the first element of 16 to D, and the first... You do realize where I'm going with this. You do realize now why they consider the Duke engine very hard to follow. Anyways, then the startup function is run, which if you go in there, we will see it configures and initializes a bunch of stuff, and then does a init engine, init timer, music startup, sound startup, and so on. And then at some point comes the main loop. Eventually display rooms, display rest, and next page is called. Now display rooms, if we go in there, we will see do interpolations, animate cam sprite, SE40 code, whatever this is, and then comes the interesting part. Draw rooms. Now, draw rooms is located in the build engine. It renders solid walls, ceilings, and floors, and also populates a list of visible sprites but does not render them. Then comes animate sprites, which is in the game module, updates the visible sprites, and then it jumps back to the build engine with draw masks. Draw masks renders the partially transparent walls like windows and visible sprites like players and items. Then comes the display rest. It draws the head-up display and the weapon. And the main loop calls next page to swap buffers. If you're wondering what is next page is a buffer swapping. Back in the days you had to be a real chat and do double buffering manually and not watch videos like what is the best Linux distro. Okay, now let's talk about how the rendering works in Duke. If you watched my Doom video, you know that Doom uses BSP trees. The algorithm reads the starting position and walks through the BSP tree. Now, in Duke, there is no BSP tree. So, how does the rendering work on a high abstraction level? First, since we are not rendering the whole map and every element all the time, as you know, prompt engineers, I'm talking to you. First, we need to determine in which sector should the rendering start. And this is usually the player sector, but since in Duke we also have mirrors, it also can be a mirror sector. So the game module provides the engine module with the sector ID. The engine module then navigates through the portal system and visits the neighboring sectors. During this procedure, walls inside the sectors are grouped in so-called bunches. These bunches are then stored in a stack of bunches. Then visible sprites in the sectors are determined and also stored in a stack. Now, after we fill the stack with bunches, which are groups of walls, it is time to render those bunches in a near to far order. This continues until the occlusion arrays are fully occluded. When it is done, the rendering stops and the game module updates all the visible sprites. Then all the sprites and transparent walls are rendered in a far to near order. And finally, the buffers are swapped with the next page function that I showed in the main loop. Now, I will go through the rendering steps in more detail. In Duke, the current sector of a player is tracked after each position update via the update sector function. So the game module calls this function all the time. Okay, so you can determine in which sector the player is by brute forcing the search. This would cost an enormous amount of processing power. So Duke does this in a very clever way. The update sector function takes as arguments the new X position, the new Y position, and the last noun sector ID. Now, the algorithm assumes that the player has not moved much since the last update. So it starts by checking the sector in which the player was the last time. And that's the one which is provided in the last noun sector ID. If that fails, the algorithm starts looking in the neighbor sectors by using portals. And if that also fails, then the algorithm goes through all the sectors with a linear search. Searching through all sectors is of course very expensive in terms of processing power. Now you're probably wondering, but Tariq, how do we know if a point is inside or outside a sector? To easier understand how the build engine does it, let me explain to you how it generally works. And that leads us to the ray crossing method. So imagine we have a point and we have a polygon. Remember, it has to be a polygon. And now we want to know if this point is inside or outside. So here is what we do. We take this point and cast a horizontal ray to the right from the test point. And now we start counting how many times is the ray crossing the edges of the polygon. If the number is odd, the point is inside the polygon. If the number is even, the point is outside. Why does this sorcery works? Well, every time the ray enters and exits the polygon, it passes through two edges. So if a point starts inside, it crosses an odd number of edges to escape. If it starts outside, it crosses an even number of edges. This is the basic idea of this method. Now we will go through the implementation in the build engine. Now, how does the engine even know if something is inside or outside the sector? In the build engine, we have this function called inside. The code per se is kind of difficult to follow, not because it is something out of another dimension, but it's more the small things like very generic variable names like x, y, I, j, and so on. Then variables are not grouped into structs, the comments are very sparse inside the code, and anyone foaming now it's a skill issue is probably unemployed and has all these misconceptions about what a day in life of a senior software engineer looks like. Talking from my experience, the more experienced the software engineer is, the easier it is usually to follow his code. You have small but significant comments everywhere that lead you through the code. They do it of course so other people can follow it easier, but they also do it for themselves. Now, if you're in a project that's going to be developed or maintained for the next 10 years, you want to save yourself the headaches of situations where you are sitting and reading your own code and you have no clue what you did or why did you do it that way. It is easy to remember the purpose of every line if you work only on one project, but if you're a good engineer, you will have to work on or maintain more than one project simultaneously. So now back to the topic. We have the inside function. The code does not have any comments in there, but we have the build info text file from Ken Silverman. So inside tests if a point xy is inside a sector secnum. It returns a 1 if it's inside and a 0 if it is not inside. Now these two sentences make it 100 times easier to get an idea what the function is about. In Doom we had the point on side function which gave you an answer on which side a point is. In Duke we have inside. Now if you haven't skipped math, you know that you can use the cross product of two vectors and then just look at the z component of the result. If it is positive, it is on the right side. If it is negative, it's on the left side. Okay, that's how you can use a cross product to check the side of a point. Before we continue, if you like the content, hit like and subscribe. Only 6.7% of my audience is subscribed to the channel. Let's try to get this to a double-digit number. Also want to take the chance and say a big thank you to my Patreons and YouTube members. Viorel Petku, Amro Ibrahim, Henry Melendez, Joey Herschel, John Stanovich, my bro Devin Piecemeal, David Ziskovsky, and my YouTube members 321 Crazy T, Elo Vasa, 0x333, T-Branch 227, Abhiyankar Shakti, Crunchy Chiro, Siafik Ashraf, Luisa Ruda, Joe Williams, Peter Iskandar, and Noah Cope. If you want to help me get better equipment, you can become a Patreon or YouTube member. The link is in the description. Now we can take a deeper look. How does the engine determine if a point is inside a concave polygon or not? First, let's imagine we have a polygon. Or you don't need to imagine, you can just look at my diagram. So we have this polygon which is built out of edges, or how the engine calls them walls. And inside the polygon we have a point A. Now the point has its coordinates x and y, and every wall in the polygon has its 2 points x, y, y1 and x2, y2. We want an algorithm that can determine if the point is inside this polygon, and we want it to be fast as possible. So this is the inside function that does exactly that. It tests if a point is inside a given sector. The sector in this case is a closed polygon. Okay, now let's walk through the code line by line. First, it checks if the sector number is valid. If not, it returns a -1 right away. Then we initialize a variable count to 0. This CNT could also mean something else. This is not a traditional counter, so we're not incrementing this count. Instead, this function uses the XOR to keep track of the parity, which basically means we are counting the number of ray edge crossings and we are trying to determine is it even or odd. Then we grab a pointer to the first wall in the sector and then we loop over every edge. Now, here is where it gets clever. Since we want to use the ray crossing method, we need to find out is the wall that we are testing even relevant for our test. The wall could be above the test point, that would mean if we cast a ray it would miss the wall, or it could be below this point. Then again, the ray would miss the wall. In that case, we want to skip to the next wall. Now, the first elegant trick is this one. This is a bitwise XOR operator. It checks if y1 and y2 have opposite signs. Stay with me now, this will all make sense and you will realize how genius this is. So first, we subtract the value of the y-coordinate of our test point, point A, from the two y-coordinates from our wall. If our point A is above the wall, it will move both points into the negative, which will then make this condition false and we skip to the next wall. If the point A is below the wall, it will make both points stay in the positive range, and again, not trigger this condition. Now, in case y1 and y2 do have opposite signs, that means that our ray from the point A will hit the wall in case the wall is on the right side of our point A, and in that case the function continues. Now we want to know from which side of our point A is the intersection with the wall happening. So again, we are subtracting the values of the x-coordinate from our point A from the two wall points. Same thing as before, just now it's left or right. If both values x1 and x2 are positive, that means the wall is entirely to the right of our point. So we toggle the count variable with the XOR. If it's negative, that means that the wall is entirely to the left of our point A. Now, here is where it gets tricky. What if one is negative and the other one is positive? In that case, we can't really tell if the crossing is happening on the right or the left from point A. I mean, it could be like this, so the crossing is left, or it could be like this and the crossing is on the right. In that case, we need to determine the exact point where the crossing happens. So we do a 2D cross product and toggle the count parity. If it is on the right, it affects the count. If it is on the left, it doesn't affect the count. So the algorithm only and only when it's absolutely necessary performs the full set of calculations to determine if the wall is crossed by the ray or not. And it does everything by using these bit tricks. When I first read the function, it wasn't intuitive at all, but now it all looks extremely elegant. Now, here's a really important case. What if all the edges of a polygon are completely to the right of the point? I mean, that could be the case. Imagine your test point is far to the left, outside of a polygon that's completely on the right side. In that case, several edges might cross the horizontal ray, but all of them do so to the right of the test point, and that's completely fine. The function will XOR those in, and if the total number of crossings is even, the point is considered outside. If it's odd, it's inside. So yeah, even if the entire polygon is to the right of the point, the test still works correctly. The important thing is whether the ray from the point intersects edge to the right of it. And then the final result is returned. So this extracts the sign bit from count. If it's 1, the point is inside, and if it's 0, it's outside. That's it. No floating point math, no explicit crossing counter, just integer math and XOR based parity checks. Fast enough for a 90s CPU and clever enough to impress us today. Okay, now let's dissect Draw Rooms, the build engine's core 3D rendering function. It is located in the engine.c file, and if you take a look at the top, we will see it starts by defining a lot of global variables. Global variables for everything. As I said, this is one of the main concepts, design decisions. We have a global state that is defined by the global variables. and all functions directly access and manipulate these variables. So the data is the interface. Okay, so it kicks off the render pass by setting up the player's view, scanning visible sectors, and rendering walls and floors using a portal-based system. It's plain old school C. No structs, no returns, just global state and raw performance. We start by assigning the player's position and angle to global variables. These globals are used by everything from geometry transforms to wall sorting, so they're set once and then you just read it everywhere. Next, the engine setups the vertical viewing range and screen space clipping plates. So this controls the pitch, whether the player is looking up or down, and defines where vertical walls will start or stop drawing on the screen. Then it computes visibility factors for shading and distance fog. This affects how fast things get darker as they recede into the distance. And now here's where we hit a subtle but super important part of the build engine, the vertical clipping. Before rendering, the engine needs to initialize which parts of the screen are actually visible per column. So it does it by using the two occlusion arrays, UMost, the highest Y pixel you can draw in each column, and the DMost, the lowest Y pixel you can draw in each column. To set up these, we first define some local pointers, and let's break down this line because it's classic C pointer trickery. So we're taking the address of the start, UMost window x1 element, the first visible screen column, and assigning that address to short pointer 1, which is a short pointer. So now short pointer 1 element 0 is start UMost Windows x1, and then short pointer 1 element 1 is startmost Windows x1 plus 1, and so on. This basically allows us to loop over only the visible part of the screen without needing to do plus window x1 math inside the loop, which would, I think, probably slow things down. And in case you're wondering why do we need this cast to a short pointer, we actually don't need it. It's redundant in this line. Okay, then we have this. This sets up the loop that populates the actual render time clip arrays, and this loop does one thing. It takes the starting vertical clip values from start UMost and start DMost and translates them into window relative coordinates by subtracting this window y1. Why is this important? Because build supports rendering into sub-windows, mirrors, viewports, head-up display views, so the top of the visible area might not be y equals 0. This subtraction ensures that the clip values are relative to the current window, not the full screen. And once UMost and DMost are initialized, they act as clipping guards. Every time a wall, ceiling, or floor is drawn, it gets clipped to this range. And when something is rendered, it can also update UMost and DMost, so it knows not to draw over areas that are already filled. So we have no overdraw. It's a software Z buffer, but only in the vertical dimension, lightweight and incredibly fast. Now back to draw rooms. Once the vertical clip buffers are set, the engine scans visible geometry starting from the current sector using scan sector, which fills a global list of walls and floors to be drawn. Then it processes the bunches by using the global arrays. So each bunch starts at bunch first. The engine then draws each bunch in front to back order by calling draw walls closest. This is critical for correctness. Since build doesn't use a depth buffer, the draw order must be exact. And again, no structs, no memory allocations, just draw arrays and pointer math. Understanding how build renders are seen means understanding how we draw walls, ceilings, and floors, top down. Now let's take a look at the occlusion arrays. So as mentioned before, build renders from the edges of the screen toward the center. That means walls and portals push rendering bounds inward. In between these gaps is where ceilings and floors get drawn. At the core of this technique we have two occlusion arrays. So we have the short UMost, which is the upper draw limit per screen column, and we have the short DMost array, which is the lower draw limit per screen column. These arrays track what parts of each vertical screen column are still drawable. As walls and floors are rendered, these arrays are updated to move to the upper and lower bounds closer together. When they meet, the column is fully occluded and skipped. Now, it's important to mention that these arrays are often only partially updated. Why is that? Well, because portals leave gaps, holes in the occlusion, so rendering can continue into connected sectors. Okay, so what happens when rendering a wall from a bunch? If it's a solid wall, we draw the ceiling if it's visible, we draw the floor if it's visible, draw the wall itself, and mark the whole column as occluded. If it's a portal, we draw the ceiling if visible, draw the floor if visible, and peek into the next sector. If its ceiling is lower, we draw a downward step. If its floor is higher, we draw an upward step. And then we update the occlusion arrays to reflect what was drawn. So this basically continues until all bunches are processed or all columns are fully occluded. Now, in my opinion, the best way to visualize how the rendering happens is to take a look at the animation that Fabian created. So let's take a look at that. Okay, now after the map has been rendered comes the sprite rendering. The engine draws the sprites with the draw masks function. That's the rough idea how the rendering works. If anyone wants to go through the source code for rendering, I would recommend reading the Chocolate Duke source code, since there are some comments. The original Duke source code has very little to none comments. Okay, that was the build engine source code. Now let's briefly take a look at the game module source code. When you open the repo where both game module and the build engine are, in the source folder, not the src folder, you can find the game module source code. Now, generally speaking, the coding style is quite different. And if you go through the files, you will also realize that inside the game module, they don't clearly follow a uniform coding style. You will see different commenting styles, different naming conventions, and so on. What you will also see is that these guys really love switch cases. For example, the game.c file has about, 3,000 lines of switch case. But what confused me the most is that in the game module, you will find a lot of files I would expect in the engine, for example, the sound functionalities. Overall, the readability is a bit better than in the build engine, but if we, for example, open player.c and we take a look at this function, you will also see stuff like this. Again, very generic variable names, some magic numbers, and this makes understanding the code kinda difficult. The same goes for the next function. You will have these type of variables, pj, kl. I guess if you spend some time in this code base, you get the idea how is everything used, but this is where I start missing some ideas of object-oriented programming. I'm not saying I'm missing an inheritance hell and it would make this better. What I'm saying is, if we group these variables in some struct and named it properly, it would make understanding the code much easier. And another interesting thing is, if we go back to the game.c file, and we scroll to the bottom, we will see some kind of sticky notes and also some kind of brainstorming here, I guess, ideas how to make the level design. So we have Death Valley, Vegas, Jungle, and then also some dialogue between Duke and a commander. This might seem boring for some, but I always look at these things like an archaeologist. This text has been written 30 years ago, and now I am reading it. It's fascinating for people who operate a YouTube channel, I guess. Okay, that's that about the game module. Now let's go a bit through the build info text file where Ken Silverman described the engine functions. One interesting thing that Ken Silverman provided with the source code is the build info text file. This file contains explanations for all the relevant functions of the engine, and also some other explanations, for example, how to properly read a map file. So in case you tried at some point to read the code and you couldn't really connect the dots of what's going on, you are not alone. So let's open the file. Okay, so as you can see, even this file was maintained over a 4-year period. First part explains the art map palette format. The second part is about the build engine functions. I want to show this file to anyone who says dumb stuff like, we don't need documentation, the code is the documentation, just read the code. No. You have no idea how much a project's success can depend on whether it's documented properly and documented enough. When you write good documentation, you are creating a shared understanding for everyone on the team. You are saving time, a lot of time, especially as new people join the project. And over time, this time saving has a compound effect. And also, let's be real for a moment. I know a lot of engineers who either don't have social skills, or they're shy, or they're scared someone's gonna judge them for asking simple questions like, hey, how does this work? Or what's the point of this function? So what happens? They don't ask, they spend 10 hours digging through confusing code trying to reverse engineer it, get it wrong, and make a bigger mistake. But if there were just 2 or 3 pages or 2 or 3 sentences of solid documentation, they would have read it quietly, not bother anyone, and just get the job done. And one last thing. I've seen good projects with no documentation, sure, but I have never seen a well-documented project that sucks. Let's leave it at that. Okay, so the file starts with explaining Ken's art format, then comes the packet format. So Ken created an own network packet format, and here it explains how the fields are defined. So you have some common fields, and then comes the message header. This kind of reminds me of the Quake network channel header. So the header contains information about the packet and what to expect on the receiving side, like send player name, movement, info, and so on. And the last field is a cyclic redundancy check. Then comes the build map format. He basically explains how to read the build map format. Very useful stuff for the modding community. And then we have the sectors, and here you again see how the sector type struct looks, but also with extra explanations on each member of the struct. The same goes then for the walls and the sprites. Okay, and now we have the important engine functions. As you can see, there are not that many engine functions. It's basically to initialize it, uninitialize it, load, save. But what I like about this is that Ken wrote 1 to 2 sentences about each function and what it does. It's not just like uninitialize engine, uninitializes the engine. But it says, okay, if you call uninitialize the engine, it frees the buffers. And you should call it at the end of the program before quitting to DOS. There is nothing that I hate more when people say to me things like, uninitialize just uninitializes. Yeah, sure, but what does uninitialize mean in your case? And that's what I mean when I say documentation helps getting this shared understanding of what a piece of code does or what it is supposed to do. Okay, let's keep going. So it continues with the drawing functions, which is basically the rendition. And while I was preparing this video, it really helped me since the code, as I said, wasn't really commented. The functions are grouped in these like kind of different topics, even though most of these functions are in the same file. So if you want to go through the source code after the video, I would highly encourage you to open this file in a second window and then go read the code. It will help you immensely. And also keep in mind this is 30 years old. The code is basically about to start hiking on the weekends and think about joining a social running group, or I don't know, start to watch and identify birds. Anyways, let's wrap this up. Conclusion. Duke Nukem 3D source code is like fighting a monster alien on a football field while blonde cheerleaders are dancing, or getting a stripper pregnant who turns out to be an alien but you take her home anyway because it's Saturday. It's raw, loud, and full of chaos, and it works. But here's the thing, nobody sees what's under the hood. Players only care that the game runs, that it's fun, and that it delivers an experience. They don't care if your code has clean dependency injection or if it violates every principle in a software engineering textbook. The build engine wasn't designed to be flexible or clean. Its goal was simple: deliver modern feeling 3D gameplay on low-end hardware. And by that measure, it absolutely nailed it. So judging it by modern standards of clean architecture or maintainability is missing the point. This wasn't a long-term code base meant to live forever. It was a product with a deadline and a very specific goal. Now, if you're working alone, you can go fast, but if you're working in a team, you need maintainability. Because when you come back 6 months later or hand it off to someone else, your clever two-liner with a weird C++ feature nobody uses is now a minefield. This brings me to something I call value A and value B. Value A is the primary value, how readable, maintainable, and extendable the code is. Value B is the secondary value, what the code actually does. And ironically, the secondary value is what everyone sees, but it's the primary value that defines whether your project can grow, evolve, or even survive. There is even literature on this. In the book The Pragmatic Programmer, the author stressed that the code should be written for humans to read first and machines second, because the machine doesn't care if your logic is spread over 10 lines or 2. It will optimize it anyway, and I have seen this in real life. My cousin once told me about his frustration doing lead code problems. He'd solve something in a normal way, then see someone else solve it in 2 obscure lines of code using language tricks he'd never seen. And he would say something like, "I will never be this good." But I told him, that kind of code doesn't win. It might look cool, but it doesn't create better products or sell more copies, or help when a crash hits users and you're knee-deep in stack traces. Anyone who thinks cleverness in code automatically makes a product better needs to grow up. I would rather take 10 simple, clear, boring lines of code over 4 smart ones that make me wonder what the hell is going on. Always. Because simple is maintainable, simple is safe, and simple is scalable. So yeah, Duke Nukem 3D source code is messy, chaotic, inconsistent in places, but what it delivered was unforgettable. And if you watched my other videos, whether it's Doom, Quake, Diablo, you'll notice that each of these classic games had a different architectural approach, a different mindset behind the code. So what matters is not whether the code is perfect, but whether it serves the vision. And Duke Nukem served the vision: loud, rude, over the top, and most importantly, fun to play. So that's it for today. If you like the content, then like and subscribe, and see you in the next one. Tariq 10x.